Hi guys, today we're looking at proofs by induction involving divisibility. Our learning intention for today is by the end of this lesson you will be able to complete proofs by induction involving divisibility. So let's try an example question. This is exercise 11.3, question 3. Prove by induction that 9 to the power of n minus 1 is divisible by 8 for all values of n where n is an element of our natural numbers. Okay, so when we're looking at proofs by induction, our step 1 is to show that our proposition or our general statement is true when n is equal to 1. So we substitute in n for 1 and show that the value we get is divisible by 8. So let f of n equal 9 to the power of n minus 1. So I'm just calling my function f of n. So f of 1 is equal to 9 to the power of 1 minus 1. This equals 8. This is divisible by 8. Therefore, it is true that our general statement holds when n is equal to 1. Step 2. We assume that our proposition is true when n is equal to k. This gives us f of k equals 9 to the power of k plus 1. And this is divisible by 8 by assumption. So we know that f of k is divisible by 8 by assumption. We now have to prove that our proposition is true when n is equal to k plus 1, given that it is true for when n is equal to k. We will do this by writing f of k plus 1 in the form of f of k, which you can see above, in the form of f of k plus some remainder, plus a remainder. And your remainder will be divisible by 8. So we need to show that this remainder is going to be divisible by 8, which means that we'll have shown that f of k is divisible by 8 and the remainder is divisible by 8. Therefore, your proposition holds true for n is equal to k plus 1. Okay, let's have a look and see what we mean. So we need to substitute in k plus 1 for n. So f of k plus 1 is equal to 9 to the power of k plus 1 plus 1. We are now going to use our exponent rules to simplify our indices. So on page 21 of our formula booklets, we're told that a to the power of n times m can be written as a to the power of n plus m can be written as a to the power of n times the same base to the power of your second indice. This means I can write 9 to the power of k plus 1 as 9 to the power of k times 9 to the power of 1 plus 1. This simplifies to 9 times 9 to the power of k plus 1. We now want to split off this function into f of k and our remainder. So 9 times 9 to the power of k plus 1. If you have 9 of these, this is the same as writing 9 to the power of k plus 8 9 to the power of k. So 1 9 to the power of k plus 8 9 to the power of k's gives us 9 9 to the power of k's. So we can split this. Okay, so we're going to split this. This gives us 8 9 to the power of k's plus 9 to the power of k plus our 1. And we can see here that 9 to the power of k plus 1 is f of k. So we can replace this with f of k, which we have assumed is divisible by 8 in step 2. So we then write f of k plus 1 in terms of f of k and the difference. This gives us 8 times 9 to the power of k plus f of k. So we know that this is divisible by 8, and we can see that our remainder is also divisible by 8. So your remainder, this value, your remainder, d, must be divisible by 8 also. Therefore, we have shown that both terms are divisible by 8. And so this is true when n is equal to k plus 1. And step 4, our conclusion is that our proposition is true when n is equal to 1. Our proposition is true for when n is equal to k, and therefore it is true when n is equal to k plus 1. And so, by induction, it is true for all values of n where n is a natural number. And this is how we do proofs involving divisibility. Okay, so when you're doing proofs by divisibility, we keep the same steps, except in step 3, when we're showing that our proposition is true for n is equal to k plus 1, you must substitute in k plus 1 for n, and then split your function into f of k and some value of d, which is divisible by the given number, which therefore proves that f of k plus 1 is divisible by your given value. Let's just remind ourselves of how we complete a proof by induction. So there are 4 steps when we're doing a proof by induction. You will be given a general statement. The first thing you must do is prove that your general statement is true for when n is equal to 1. Your second step is your assumption. You assume that your general statement is then true if n is equal to k. Step 3 is your inductive step. You must show that your general statement is then true for when n is equal to k plus 1. And step 4, your conclusion, is then that your general statement must be true for all positive integers n because it is true when n is equal to 1, true when n is equal to k, and true when n is equal to k plus 1. Okay, this time our general statement will involve showing that our equation is divisible by a value given. Let's look at an example. Prove by induction that 3 to the power of 2n plus 11 is divisible by 4 for all positive integers of n. Okay, step 1, we need to show that the proposition is true when n is equal to 1. This means we substitute in n for 1 and show that the value that we find is divisible by 4. So substituting in n for 1, we get 3 to the power of 2 times 1 plus 11, which gives us 3 squared plus 11, which is equal to 20. 20 is divisible by 4, and therefore this is true for when n is equal to 1. Our step 2 is to assume that our proposition is true for when n is equal to k. So here we assume that it's true when n is equal to k, so wherever we see n, we substitute in k. This gives us f of k is equal to 3 squared times k plus 11. By assumption, this is divisible by k when k is a positive integer. In step 3, we must prove that the proposition is true when n is equal to k plus 1, given that it is true when n is equal to k. To do this, you must directly write your general statement f of k plus 1 in the form of f of k plus d times your general statement by splitting off f of k, or some multiple of it, and where d is the divisibility number. Let's have a look at how we do this. We substitute in f of k plus 1 for n into our general statement. This gives us f of k plus 1 is equal to 3 squared times k plus 1 plus 11. We will now simplify this exponent. 3 squared times k plus 11 gives us 3 times 2k times 3 squared. This is because, using our exponent rules, a to the power of n plus m is equal to a to the power of n times that same base to the power of n. So I'm just splitting up my exponent here. Simplifying this gives us 9 times 3 to the power of 2k plus 11. We are now going to split off f of k. So we have 9 3 to the power of 2k's. So this is the same as writing 3 to the power of 2k plus 11 plus our remaining 8 times 3 to the power of 2k. So I have 9 3 to the power of 2k's. We split this into 1 3 to the power of 2k plus 8 3 to the power of 2k. So you split off this value. We are then left with 3 to the power of 2k plus 11 plus 8 to the power of 3 to the power of 2k. Our first value here is f of k plus 8 times 3 to the power of 2k. We then write f of k plus 1 back in terms of f of k and the difference. So we know that 8 is divisible by 4. So we can write this as 4 times 2 times 3 to the power of 2k. We have therefore shown that f of n is divisible by 4 when n is equal to k plus 1. Our conclusion states that our proposition is true for n is equal to 1. Our proposition is true when n is equal to k, and our proposition is true when n is equal to k plus 1. Therefore, by induction, it is true for when n is any natural number.